Hi, welcome to this lecture on mathematical methods. We have been discussing diffusion and we talked about the diffusion constant and the current due to the concentration difference. Today our topic is understanding diffusion constant. The topic is diffusion constant, Einstein relation 1905. And the question we will answer is, how did Einstein derive a relation for a diffusion constant? So, the thing that we learned, which is the d, which was a part of this equation, which is the current or the flow of proteins due to diffusion. When you have a cell or a tube having a high concentration at one end and a low concentration here, there will be a flow in this direction, and this flow J, this is a diffusive flow due to diffusion, is minus d del C. So, this is something that we said, and we find out that the dimension of d or the unit is meter square per second, but what all d depends on? What is d? What are the things that d will depend on, the diffusion constant will depend on? So, this is a question that Einstein tried to answer in a very famous paper in 1905, Einstein's paper, Einstein. So, some of you would know that Einstein wrote many famous papers in the year 1905. It's called a miraculous year because one person produced so much work in that one year. So, in that miraculous year, he also wrote a paper on the Brownian motion. So, what is Brownian motion? Brownian motion is essentially diffusion of particles, or it is related to the diffusion is related to the Brownian motion. So, because of the temperature, since the temperature is 300 Kelvin, around 300 Kelvin in biological system, and the room temperature is around 300 Kelvin, the water molecules in the cell, for example, would be doing a zigzag motion, and because of that they will go and hit the proteins, and the proteins will move around, they will jiggle around, and this would lead to some kind of random motion, and this is the basis of diffusive motion. So, using idea from statistical physics, kinetic theory, Einstein thought about this and derived a relation for diffusion constant d. So, we would see how Einstein derived it. It is so simple that it is application of the calculus that we learned so far. If we apply that, we would get the ideas we learned so far. If we apply, we could get some idea on how Einstein got this relation for d. It is, so we will see that how this was obtained in this lecture. So, let us think about this. So, for that, let us consider the following case where we have a container. It's like a test tube, in which of course there is water everywhere. So, there is water at 300 Kelvin. So, the water at room temperature or at some temperature T. So, this is water temperature T, and of course water has a viscosity, eta is a viscosity. So, these are the property of the water, and then now you put a lot of molecules in this, which is much bigger than water, and they will come down, because of gravity. The gravitational force will pull them down. So, this is something that we all know, that this will pull down, and there is a flow of these protein molecules from top to bottom. It will sediment, and this flow, which we can estimate, and the flow due to gravitational force, which is Jf, which we know that is C times V, where C is the concentration and V is the speed with which this would come, and this V is related to the force, and this can be written as Cf by 6 pi eta A, where A is the radius of this particle. So, these are protein red is, so this red things are protein molecules or proteins slash other macromolecules. It could be protein or it could be anything. Macromolecules having radius A. So, these are, we assume that they are like a sphere, therefore, we can say that they will flow down because of the force. So, the force here is the gravitational force, and because of this gravitational force they will come down. So, that is something that we know. Because they come down, they will sediment, so there will be a sedimentation, and after some time if we look, they all will be down and a few of them will be below also. So, they will all come down and sediment at the bottom. So, if you look at after some time t, what one would get? One would get that one would get a picture which is, I wouldn't draw the water now, I would only draw the protein molecules. So, there will be like mostly at the bottom and few here and there. So, there will be mostly here at the bottom and a few here. So, I would call this as x direction. So, let us call this as the x direction, and there is a force in this way, and because of that there will be also a flow in this way, and they will all sediment down. Once this happens, you have a higher concentration here and lower concentration here. So, when there is a higher concentration here and a lower concentration here, there will be a diffusive flow in the opposite direction. So, there will be a flow due to force F in this way, but there will be a diffusive flow Jd in this direction. So, there will be a flow due to external force, which is sedimentation in this way, and there will be diffusive flow in the opposite direction from higher concentration to lower concentration. So, what is the diffusive flow? The diffusive flow we know, which is written as Jd, which is minus d del C. So, let us do, imagine this is a one dimension x. So, let us write this minus d del C by del x along x cap, which is this way, and so this is the diffusing current, and the other one which the current downwards, which we already know, which is C F by 6 pi eta A. So, we know these two currents. One current is due to, one flow is due to the external field, which will bring this protein down, and once they are down, they will go up, and this would be the diffusive current from higher concentration to lower concentration, and this is given by this. Now, what is the C at equilibrium? What is the concentration at equilibrium? So, it turns out that an analysis will show that higher concentration at when x is at here and lower concentration here, and it can be argued, which I wouldn't discuss how it is coming, but from statistical thermodynamics and from other ideas, one can show that C of x, concentration as a function of x. So, that is concentration as you go along x would be some concentration C0 e power minus Fx by kBt. So, Fx is the energy, force times distance, and kBt is also energy. So, it can be shown that the concentration at any point, so concentration at far away, so this is x equal to 0, so there will be very high concentration here. So, n x equal to 0, here the concentration is C0. So, at x equal to 0, that is at the bottom, there will be high concentration, so which will be C0, and as you go the concentration will decrease. So if I plot C of x versus x, it would be an exponentially decreasing concentration like this, where this is C0 and this relation is C is equal to C0 e power minus fx divided by kBt, where f is the force and x is the distance, and this would be the profile of concentration. That means high concentration at the bottom, x equal to 0, and very low concentration as you go along x upward. So this can be shown from statistical thermodynamic arguments that the concentration profile will have this. So known this, Einstein knew this, and known this, so we know three facts. One, we know that there will be a flow. So so let us consider three facts that we know. What we know that there will be a concentration gradient, and there will be a concentration lower, very high concentration at the bottom, and smaller concentration at the top, and there will be a flow down due to the force. The molecules will be pulled down by gravitational force, and there will be a flow in this way because of the diffusion, and the concentration is C0 e power minus fx by kBt, and we know that Jd is minus d del C by del x. This is the magnitude, and this will have the magnitude for this would be Cf by 6 pi eta a. So we know this. So now what one has to do is that at equilibrium, when the system is in equilibrium, this flow will balance with this flow. So that is, if this is equal and opposite, the directions are opposite, and if their magnitudes are equal. So whenever their magnitudes are equal and the directions are opposite, so f will have a direction which is minus x cap. So this is f. If I put a vector sign, so let us put a vector sign carefully. So this would be x cap here, and this would be below towards the minus x. So I would write x cap with a minus sign. So this would be coming down towards minus x. F is the magnitude of the force, and x cap is the direction. Minus x cap is the direction of this diffusive flow. So if whenever their magnitudes are equal, so that is this magnitude is equal to this magnitude, there will be, when this flow will balance. So when these flows balance with each other, what will we get? So let us equate these two flow. So if you substitute this C here, we can show that Jd will be equal to minus d del C by del x. So C is this. So if the derivative of this would give us, so if I calculate del C by substituting this C here, and if I calculate the derivative of this, what I would get? I would get that d by dx of C0 e power minus fx divided by kBt. That's what I would get. So let us recalculate these two things. So let us first recalculate Jd. So what we know that C is C0 e power minus fx by kBt. That's what we know. And minus d dc by dx would be d by dx of e power minus fx by kBt, and there is C0 here. This would give C0, derivative of this would give you e power minus fx by kBt, and a factor which is minus fx by kBt will come. So times minus f by kBt. So this would be this, and if I substitute the full JD would be minus d times, this thing is my C itself, so C minus f, so this would become plus f by kBt, and there will be an x cap here. So this will be the diffusive current. So JD, if I substitute JD is equal to minus d del C by del x, since I took a ordinary derivative here because it's only function of x, I would get minus d C, this would be C, dc by dx with a minus f by kBt, minus and this minus will cancel and become a plus f, plus sign here. So dcf by kBt along x cap will be the current. And the other flow which we already know is that Jf is minus C f by 6 pi eta a x cap. So if they are the total, if they are equal and opposite, so one has to equate these two, and they have to be equal and then they have to be opposite. So if I equate this and consider them equal and opposite, I can equate these two, and with a fact that they are opposite, so I can essentially equate the magnitude of this. So if I equate the magnitude of this two things, so that is, let us equate the magnitude of this, which is dcf by kBt, and the magnitude of this, which is Cf by 6 pi eta a. So if these two are equal, this currents will be equal in magnitude and opposite in direction. So this is along the plus x direction, this is along plus x direction, this is along minus x direction. So if these magnitudes are equal, whatever I have put in this circle, in this is the magnitude. If they are equal, magnitude will be equal, the direction will be opposite. So the flow, that is, will be equal in magnitude but opposite in direction. At that, when they are equal in magnitude and opposite in direction, both the flows will cancel, and on average the number of proteins at any point would remain a constant. So let us equate these two, this equal to this. So what do I get? If I equate these two things, I would get dcf by kBt is equal to Cf by 6 pi eta a. So this would, C and Cf would cancel, and this would tell me d is equal to kBt divided by 6 pi eta a. This is the famous Einstein relation. So Einstein showed that d, which is the diffusion constant, is equal to Kb, where Kb is the Boltzmann constant, T is the temperature, eta is the viscosity, A is the radius of the protein, assuming that it has a spherical shape. So the folded globular proteins, one can approximate to a sphere which has a radius of size A. So one can show from simple calculus that by equating the current which is flowing, the diffusive current up and the flow due to force down, if I equate these two, which are this and this, if I equate these two assuming this C is equal to C0 e power minus Fx by kBt, I would get this, that these are the two currents Jf and Jd, and their magnitudes are shown here in this circle, here I have circled it, and if I take these two quantities and equate them, their magnitudes will be the same. If their magnitudes are equal, they will have opposite direction. What does that mean? That means at any point x, there will be a flow down which is equal to flow up. That means on an average, at any point x, the J here is equal this way and equal this way. If they are equal, they are on an average, the number of particles will remain a constant at any point in x, and that is the equilibrium. And at equilibrium, one would say that at equilibrium you would get a relation, and that relation is the famous Einstein relation, which says that D is equal to kBt 6 pi eta a. So, this is the important relation. So, now let us understand this. D is proportional to temperature. Higher the temperature, more the diffusion constant. Lower the viscosity, higher the diffusion constant. Higher the viscosity, smaller the diffusion constant. And A, the bigger the particle, smaller the diffusion constant. So, this diffusion constant depends on primarily three quantities: temperature, viscosity, and the size of the particle. Now, let us calculate this kBt for a typical biological molecule which is of our interest. So, let us take some protein, like let us say actin or any protein of our interest, which has size of the order of few nanometers. So, let us take A, approximately 1 or 2 nanometers. So, if I assume diameter of 2 nanometer, it will have a radius of 1 nanometer. So, let us assume if you have a small protein which has a radius of 1 nanometer at 300 Kelvin, what would be, or 310 Kelvin? Let us take 300 Kelvin for convenience, which is room temperature, approximately close to room temperature. What would be the diffusion constant? So, let us calculate that number here. So, the number D we would calculate, D is equal to kBt by 6 pi eta a. So, if you assume water, viscosity of water we have to substitute, Boltzmann constant we have to substitute, temperature we have to substitute. So, approximately the Boltzmann constant has approximately this has 1.4 times 10 power minus 23 in SI units. That is what the approximate number, and temperature is 300 Kelvin, and 6 pi is, let us take approximately 20, which is around 18 point something, but let us take 20 as order of magnitude. If we calculate eta, which is viscosity of water, and it is going to be 10 power minus 3 in SI units, that is viscosity of water in SI units is 10 power minus 3, and A is of the order of nanometer. So, in SI units, nanometer is 10 power minus 9 meter. So, everything is in SI units. So, if I substitute everything in SI units, I should get the SI unit of diffusion, D is meter square per second. So, I should get the answer finally in meter square per second. So, let us do this, so this is diffusion constant. What are we calculating? We are going to calculate diffusion constant for a protein of size, that is radius 1 nanometer in water. That is what we are calculating here. So, diffusion constant for a protein of size 1 nanometer in water. So, if I substitute here, what I would get is that 3 into 1.4 is like 4.2 into 10 power minus 21 divided by 20 times. This is 12, 10 power minus 12. So, this is 9, and there is a 20 here, and this. So, this is approximately so this would be 10 power minus, I multiply with 10 power minus 11. So this would be 10 power minus 10 2, so there will be 2.1. So 2.1 into 10 power minus 10 meters square per second. So this would be the approximate number. I urge you to calculate it. This is approximately, I urge you to recalculate this. So this would be the typical diffusion constant for a protein having a particular size of the order of 1 nanometer. So roughly 2 into 10 power minus 10 meters square per second would be the approximate diffusion constant for a particle having size 1 nanometer. So this is, we now know how to calculate diffusion constant for any protein. The only thing we have to know is rough globular size of the protein, the radius of the protein globule. If I know that at room temperature in water or whatever viscosity you take, if we take the viscosity in a cytoplasm, we would take slightly higher viscosity, roughly 5 times higher, then you would get a slightly different number, which is 5 divided by 5. So it will be like 5 times less than that. That is the only difference, but approximately roughly of this order. So we could now calculate the diffusion constant. So to summarize what we learned that one can very easily derive Einstein's relation by just doing the following: by considering protein molecules in water, they will come down due to the external force, there will be a flow, they will go up due to diffusion, and when these two currents are equal and opposite, right, when these currents, their magnitudes Jf is equal to Jd, but they have an opposite direction. So if then their magnitudes are equal, then the directions that we know already, the directions are opposite. So when they have equal in magnitude, by equating these two things, we can get that is, if you equate Cv is equal to d dc by dx, where C is equal to Z0 e power minus fx by kBt. By equating this, we got this relation d is equal to kBt by 6 pi eta a, and we computed this. This is the famous Einstein relation. This relates diffusion coefficient to temperature and viscosity, and this we calculated, which was approximately 2 into 10 power minus 10 meters square per second for a protein of 1 nanometer. So this is the summary of this lecture. With this, we will stop and continue in the next lecture. Bye.